Hi, I'm Ben-Yaakov. This presentation is entitled High Frequency Magnetic Core Losses. There are a number of core types. For example, there is the solid core, primarily made of ferrite material. This is used for transformers. There is a solid core with an air gap, and there is a powder core with a distributed air gap, like this. And then we have the wound cores, which are made of ferromagnetic material, which is fairly conductive, so therefore they have to be formed into very thin layers like a ribbon and then wound around. Faraday law states that the voltage is related to the flux, magnetic flux, by N times the phi dt, or since the flux is B, magnetic flux density times the cross-section area of the core. This is here's the cross-section area. And then V will be equal to N, number of turns, AE, cross-section area, dB dt, the rate of change of the magnetic flux density. Now I'll be using SI units, means that length is in meters, and we use volts, amps, seconds, and Henry. Flux, magnetic flux, is in Weber. B, magnetic flux density, Weber per meter square, which is Tesla. And then manufacturers are using the Gauss. Gauss is a non-SI unit. 1 Tesla is 10,000 Gauss. The relationship between the magnetic field and the current is given here. Magnetic field is equal to the number of turns on a core times the current fed to it over the magnetic path length. This is the magnetic path length. Magnetic cores made of ferromagnetic material exhibit a loop type behavior, hysteresis loop behavior. That is, if I start exciting the core, say by feeding a current, the H goes up, B goes up, and when I return in a different path. The difference here is actually this loop here that I'm going through, and this loop could be a major loop, as shown here, when I go from saturation in one direction to saturation to another direction, saturation in terms of the magnetic flux density, or it could be a minor loop, that is, I'll go around a given operating point, and in both cases I'm going to go through a sort of a hysteresis loop, either a local loop or a big one. Since the magnetic field is a function of current and B, or delta B, is a function of voltage, then the product of them, that is the area, is in units of power. And indeed, as we go throughout these loops, either the major, certainly, or even the minor loop, we are losing power. So this means that when this loop is wide, we're going to lose a lot of power. The power is lost to heat, so that this will cause a temperature rise of the core. Manufacturers give this type of a graph for the hysteresis loop. It looks strange because the units here, or the scale, is different than the scale here. So this part is a magnified scale, while here they're trying to show the behavior up to very high magnetic fields. Now notice that we have saturation here, which saturation is a function of temperature. This will be like 25 degrees, this will be 100 degrees centigrade, and the value of the saturation is around 400 millitesla for ferrite. This is a typical value for B sat, for the saturation level. Now the reason for the hysteresis loop, is the fact that the ferromagnetic material is built of magnetic domains, which, as we increase the excitation, magnetic field, they are rearranged inside the material, and this rearrangement entails, so to speak, some friction, and this friction brings about this magnetic loss. Why do we have to worry about losses in the core? Well, first of all, of course, the efficiency will go down because we are losing power to heat, and there is less of the electrical power. But more important is the question of temperature. Due to the losses, the temperature of the core, and therefore the device itself being a transformer or a inductor, the temperature will rise, and this may require actually a heat sink if the temperature is too high. It will cause or may cause damage to insulation if the temperature is over the safe limits of the insulation. And finally, if the temperature goes very high, we may reach the Curie point or Curie temperature, and this is the temperature at which the ferromagnetic material is actually losing its properties, ferromagnetic properties, and this is of course very dangerous because suddenly we don't have any more magnetization, and it'll be like windings in air. An important parameter or term that is used is the hot spot, and this is the highest temperature within a magnetic structure. For example, a transformer or an inductor, this will be the hottest point, and this will be typically inside where the thermal resistance to the outside is the highest. Manufacturers are providing information about the magnetic losses in charts like these. These are based on the fact that it was found experimentally that the power loss of a given material is a function of, say, a constant times frequency to the power of n, and then delta B, that is the deviation of the magnetic flux density to the power of m. M and n are numbers, constant numbers for any given material, and these are found by actually curve fitting. So what we see here this is the deviation of B, and this will be the peak value when the excitation used to measure these constant is sinusoidal and around zero. There is no bias, and it's an AC signal, and this will be the Bmax of this signal. So it'll be a 10 millitesla, 100 millitesla, etc. Here we have actually the power loss in units of kilowatt per meter cube, which is the SI unit. Kilowatt is 1000 watts per meter cube, and kilowatt meter cube is actually milliwatt per centimeter cube. These curves are given now for different frequency, because frequency is the dominant parameter here. So this will be 25 kilohertz, 100, 200, etc., up to 1 megahertz for this particular material. This is for Ferrous Cube company, and this is a 3F3 material, and all these are given for 100 degree centigrade. So if we know what is the delta B that we have, then we can sort of bring this curve up, and for the given frequency that we are operating, say it's 100 millitesla that we are operating at, and the frequency is say 200 kilohertz, then we are at this point, which is about say 180 kilowatt per meter cube. And this will give us the information about the power loss of this particular material. Similar curves are given for all other type of material. This is, for example, for a powder core. This is a cool mu of magnetics. We see similar curves. Here's the experimental or the curve fitting equation. Here it says flux density in kilogauss. Again, 10,000 kilogauss is 1 Tesla, so this will be up to 1 Tesla. Now, it says flux density, but this is incorrect. This is not flux density, it's a delta B. This is deviation of flux density. That is subtracting the DC value. DC value does not affect the losses. Indeed, if you move across the hysteresis loop curve to a higher value, this curve may change a little bit. There isn't enough data about how this changes, so we use this information even if there is a bias. But again, the curves are for delta B and not for the total flux density. And again, we have here the loss density. In here, it will be milliwatts per centimeter cube. Okay, so these are really very similar, except of course the value will be dependent on the material itself, like this is a cool mu, which is a powder arm core. Another bit of information which is very important is the dependence of the losses on temperature. And they are given for different operating conditions. For example, here we have delta B of 100 millitesla for a frequency of 200 kilohertz. This is this curve. And then we actually go to a lower delta B or Bmax in a sinusoidal excitation. The losses should be lower, but then we go to a higher frequency. But as it turns out, the net effect is that this lowering of delta B is more important than the increase in frequency, and the total loss is actually lower. An interesting feature of this curve, this particular curve, that it has a minimum, like here and here. It means that if you say work under these conditions, it'll be actually better to allow the core to reach a temperature of 80 degrees centigrade, because there is a minimum here in the losses. So, contrary perhaps to intuition, in this particular core, it's best to operate under condition in which the core is actually getting a little bit hot and getting to a higher temperature, and then the losses will be actually lower. Another feature that should be observed is that here we have an increase in losses as the temperature goes up. This could be very dangerous because this is actually positive feedback. That is, as the losses increase, the temperature increase, and the temperature increase, the losses increase. So if this positive feedback is just strong enough, this could cause a runaway, a thermal runaway, and a destruction of the device. So this is something to watch. Information is also given in ways of tables. In here, for example, again, I'm just using this 3F3 as an example. There's no solicitation here, of course. For example, this losses for 100 degree, 100 kilohertz, delta B of Bmax of the AC excitation, I should say, 100 millitesla, it will be lower than 80 kilowatt per meter square. And here's for another condition. Interesting information is here. This is raw. This is the resistivity of the ferrite. And it is 2 times in units of ohms meter. This is units of resistivity. Just as a comparison, copper resistivity is 1.7 to 10 to the minus 8 ohm meter. So the resistivity of the ferrite is 100 million times larger than that of copper. So this means that the ferrite is actually acting like an insulator. There's very little electrical conduction going on there. So eddy currents could be ignored. And here is one more bit of information which is kind of important in helping to choose between the various materials. Here are the various ferrite materials. This is the 3F3 we've shown before. Here the 3696, 3F4. These are different materials of the ferrite made of different composition. And here we see this is the figure of merit. This is F times Bmax, while here we have the frequency. Well, what is this figure of merit? This figure of merit is really very important because when you are calculating the core that you need from basic information like the current and the voltage in the case of a transformer to come up with this area product. The area product is the area, cross-section area of the core times the area of the window of the core where you put the windings. This product is very important in helping you to choose the core. And then you'll see here, at the denominator, we have frequency times delta B. So this product is very important. As the larger it will be, the smaller will be AP and the smaller core you need. So therefore, you like to have this figure of merit, this product F type V maximum, as large as possible. So if I compare, for example, 3F3 and say 3619, obviously 3F3 is better choice for this particular frequency. This is in megahertz, so this is, let's say, 200 megahertz. On the other hand, if you go to very high frequencies, like say 3, 4 megahertz, this material 4F1 is obviously better. So this is a way to look at the differences between the core material and to choose the one that you actually would like to have in terms of minimum size of a core. The comparison here is actually made for one particular power loss point. This is 500 milliwatt centimeter cube. So they are compared on basis of the same reference level. There is also an experimental equation, sort of a curve-fitted equation, which tells you what is the temperature rise you'd expect in a magnetic device, the inductor or transformer, as a function of the total power loss. Now, total power loss is, of course, the magnetic loss we've been speaking about, but also the copper loss. That is due to the current passing through the wires, which have certain resistance. So I square R is, of course, the copper loss, or the wire losses. You have to add these two. And what this equation is telling us is what will be the highest temperature within the core given the total power loss, surface area of the device, that is the whole area around, and this ratio to the power of 0.833. This is again a curve-fitted equation, experimental equation, just gives you an information about what is the temperature that you would expect. If I compare different materials, this will be the ferrite material. This is just an example, 3F3. This is a powder material. This is the cool mu that we've also seen before, and a amorphous core, which is a ribbon bond. And the nice feature of it is that it has a Bsat very high. This is 1 Tesla as compared to 0.5 Tesla for a ferrite and the iron powder core. So if I compare these two, for say 100 milliwatt per centimeter cube, we'll find that, say, for 100 kilohertz, the ferrite will allow us to work at 120 millitesla peak excitation. In the case of the powder core of this particular material, it'll be 40 millitesla. Again, this is for given core with these permeability values. And in the amorphous core, it'll be only 28 in the 100 kilohertz. So the penalty that you have here, although you have very high value of magnetic flux density saturation, you cannot utilize it, as a matter of fact, if you are operating at high frequency. So these cores are actually more suitable for lower temperatures, say 10 kilohertz. So the question is, how do we calculate delta B so we can estimate the losses of the core? Now we start off with this relationship. V is equal to N times AE, the cross-section area of the core, dB dt. We take the integral, and since in application of power converters, PWM, V is constant during each part of the cycle, we can assume that V is constant, and therefore we get that V delta T is N AE delta B, or that delta B is 1 over N AE cross-section area of the core, V delta T. Now I'll define this V delta T, this product, as volt second. And as it turns out, this is indeed the key factor for calculating delta B, because delta B is just a factor times this parameter. So once you know what is the volt second of your inductor or transformer, that's it. You really don't have to involve any of the current or delta I. It's enough to deal only with delta B, and this brings you the information that you need. So all that you have to find out in a particular situation is what is the volt second imposed on the inductive element. So let's see some examples. Here is a buck converter. We have a switch, a diode, an inductor, and then the output section. When the switch is on, we have on the inductor V in minus V out. Here is the on time of the switch, and this is the voltage on the inductor, here V in minus V out. When the switch is off, current is passing through the diode, assuming zero voltage on the diode, so the voltage on the inductor is minus V out. Now, in every inductor or transformer, the area positive is equal to the negative because the average voltage on these elements must be zero for stable operation, otherwise the current will drift. So this area is equal to this area, so that for the volt second, which is just this area, we can calculate either here or here. So if we know the on time, which is d duty cycles times the period, we know this on time times the height, this is the area. Now, the maximum volt second that you'll get is when this moves, the duty cycle becomes very, very small. This will be for a very high input voltage, then the on time will be very small, and off time will be almost 1, and then this area will be the maximum that you will get in the case of a buck converter. So the maximum volt second that you will get is V out over T, the period of the switching cycle. So once you have this, then of course you get delta B by multiplying with the relevant factor. Another example is the boost converter. Here we have, when the switch is on, we have V in. When the switch is off, we have V in minus V out. So when the switch is on, we have V in. When the switch is off, V in minus V out. This is, of course, the voltage across the inductor. It's not labeled here. So in boost, we have V out is V in over D off, or V in is V out times D off. Now we can calculate the area here to be V in times the time. The time is the duty cycles times the period. So and I also put V instead of V in, V out times D off. So I'm getting that the value is V out times D off, D on times T. So this is actually the volt second calculated from this area here, which of course is equal to this area here. Now you have a product here, D off times D on, and of course D off is 1 minus D on, and therefore when D off is approaching 1, D on is small, and vice versa. When D on is approaching 1, D off is small. And as it turns out, the maximum value of this, when D off is 0.5 and D on is 0.5 and the product is 0.25. So you can say that in the case of the boost converter, the maximum volt second that you will have is 0.25 V out times T, the period of the switching cycle. Very simple. Once you have, of course, the volt second, you get delta B. And finally, I'll give you an example of a transformer. In a PWM, a transformer will be fed by a signal or by a voltage that looks like this. Here it is. There's some maximum value, and then there is a sort of T on duration, which is, of course, the duty cycles times the period. Now, since B, the magnetic flux density, is the integral of V dt, then therefore, as long as the V is constant, B goes up linearly, and then it goes down linearly when the V is negative. Value of delta B is 1 over N AE, which is the cross-section area of the core, VMD times T, and the highest value that you'll get will be when D approaches 1, and then it will be 1 over N AE VM times T. So it shows that once you know what is the volt second that you are dealing with, it's very easy to find delta B. Once you know delta B, you go back to the data and get your losses for the particular core that you are using. This brings me to the end of this presentation. I thank you very much for your attention. I hope you found this presentation interesting and it will be useful to you in the future. Thank you.